general ideas of things that we could establish when somebody put one of these equations in front of us. So first thing, vertical asymptotes. How do we find them? Damien. No? Okay. Somebody else. That's right. Okay, so for the ones we worked on like 2 days ago where x was only in the denominator, you just looked for a horizontal translation left or right to move the asymptote from 0. But what's a rule of thumb that we can use to find the vertical asymptote of any rational function? Because that only works in the ones where it's like 3 over something with x or 1 over something with x. That's it? Good. When the function's undefined. How do you find values of x that would make the function undefined? Keelan? Good, when the denominator equals 0. So those are two very important concepts, like what it represents and how to find it. So vertical asymptotes represent where the function is undefined. We find it by finding x values that would make the denominator of the function equal to 0. Does that make sense to everybody? Okay, so to review that a little bit. All right, horizontal asymptotes got a little bit more complicated, right? This is all that stuff that we worked on in that chart yesterday was to figure out what was going on with the end behavior or the limits of the graph. All of that stuff is related to horizontal asymptotes. So when you look at a function, what is it that you're looking at to help you determine the horizontal asymptote? Anna? Good. So if you need more clarification. Okay, we're going to look at the degree, and it fell into 3 cases. What were our 3 cases? Damien?
Numerator is greater than denominator.
Okay.
Numerator is equal to denominator.
Okay.
Numerator is less than denominator.
Good. All right. So you look at the function. You decide which of these categories it's in. Okay? So let's say you're looking at a function where the numerator is greater degree than the denominator. What does that tell us about horizontal asymptotes or the end behavior of the function? Good. There is no horizontal asymptote, which means our function does not settle down at one number at the end and become looking horizontal. Instead, it shoots up or it shoots down and follows some other function. Okay? Then what we said was this is going to mean you're going to have to go find an oblique asymptote, and we'll talk more about that in a minute. Okay? All right, what about when the numerator was equal to the denominator? So let's say you look at your function, you find when it's undefined, so you have vertical asymptotes. You notice it has equal degree in numerator and denominator. How do you then find the horizontal asymptote that will describe the end behavior of that function? So when they were equal, what did we look at? Jarrett? Good. So this does have a horizontal asymptote. It's y equals some number, and this number is going to be different depending on how the function was built. And just like Jarrett said, this number is based on the ratio of the lead coefficients. Okay? All right, third case. You're looking at the function. And instead of any of these other things happening, the denominator has the highest degree. What does that tell you about your function's behavior? I see Keelan and Jarrett, but they both already gave me an answer, so just like. Good. It does have a horizontal asymptote, and every time it's at y equals 0, despite the numbers in the function, if the denominator has a greater degree. Okay? So vertical asymptotes, you find them the same way every time. Horizontal asymptotes really depends on the cases, which is why we had to look at all those different types yesterday and kind of wrap our head around the idea that there are different kinds of rational functions and they behave differently. All right, so we said we're going to get more into oblique asymptotes later, that we should only have an oblique asymptote if we don't have a horizontal asymptote. So remember, both of these things here describe end behavior. if your function is becoming horizontal at the ends, there's no way it's also oblique at the same time. Okay? If it's horizontal, it's flattening out. If it's oblique, it's saying it's not flattening out. It's either going to go like a line like this where one side shoots up and one side shoots down. Maybe it's going to go like a parabola where the ends of it both shoot up. And we'll find out those things doing what? What did we say we were going to use to find an oblique asymptote? We didn't delve into it, but we just said we would use it. Divisions. We're actually going to go through and divide those equations. So to find these, we would use division. All right, holes. So when we looked at a couple of examples of what the graphs could look like, you saw a graph that looked like a line with a hole in it, and we discussed a little bit how something would show up as a hole instead of a vertical asymptote in our graph. So what did we decide? What about the equation is going to let us recognize that there is some sort of hole in our graph? I'm going to go back to the slide that we looked at that had graph pictures. So this graph had a hole right here. Okay. Why did that graph have a hole there? Good. Because that was an x value which the denominator equaled 0. Why a hole in this graph? Why distinctly a hole? Instead of when this denominator equals 0, we put a vertical asymptote at that point. Alicia? Okay, so the line does go through it, but that's not exactly why it manifests itself like this instead of like this. Damien? Good. Okay, and it came down to some of these vocabulary words down here too. Okay. In the equation, can this factor be removed when you simplify the equation? Yes. Okay. Then what's happening here is you have a removable discontinuity, something that's going to break your function because you can't plug in that number, but in the equation, it like cancels out. It's removable. Is this factor removable if you simplify this equation? No, there's no x minus 2 in the numerator that cancels that factor. So it's not removable, and they look differently on the graph. If it's removable, we mark it with a hole. If it's not removable, we mark it with an asymptote. Okay? So going back to how we're going to find holes in our graphs, is we're going to look for factors that cancel from the numerator and the denominator, because if those factors can be removed, we know that because it was in the denominator, it would make the function undefined. Since it can be removed, it's one of those removable ones. Therefore, it's a hole and not an asymptote. Okay? So if I was going to make a note for myself, and you can word it however you want, I would tell myself to look for factors that cancel, and maybe I would give that equation that we saw earlier as an example. Okay. That those cancel. So what this means is that we would graph what's left, and then we would just also have a hole at that special x value that would have made that factor undefined. Does that make sense to everybody? So that's how you can identify holes, by looking at your equation. Okay. So you'll take an equation like this. If something cancels, that should be a red flag to you that says there is a hole. Okay. Then you're going to go graph whatever's left, just like you normally would. Maybe it's not complicated. Maybe it is complicated. Finish the graph. Then take your eraser and go to this point that would be on the graph for that x value and erase it so that you have a little hole. Okay? Just like one factor. So if this function had had more factors in it, like let's say it also had a factor of x minus 5 here, right? And this canceled out. Then I would go graph whatever x plus 3 times x minus 5 looks like, some quadratic. And on that quadratic, I would still go on the x-axis to -2 and go to that point on the graph and erase it. Okay? Awesome. So if there was more factors in the denominator, that's okay too. Let's say there was like different than the ones in the numerator. Say there was an x plus 1. Then you're going to graph this. This is going to be one of those, could look lots of different ways, right? You'll still finish graphing in it, and at the end, you'll go create that whole. Okay? All right, don't do homework number 6 tonight. Thank you. We'll finish discussing this tomorrow, and then we'll start the homework in class, okay?